One of the most important features of any CAE package is its post-processing abilities. This is what your customers are going to see. This is what your management sees, and it really helps you to see what the issues are in your problems. So here we see ElectroFlo has no shortage of post-processing capabilities. We can see the three different 2D windows here. You can include the fluid in your plot, or you can just have velocity vectors displayed for the fluid. You can also add labels, and then these labels will automatically adjust to any plane that you jump to. You can keep your spectrum as your full model, or just look at it for plane. As you can see, the spectrum actually changes as we go from plane to plane here, as the labels are also adjusting. We do have full built-in 3D post-processing, and you can see your model in great detail there. While that's up, you can hide anything, and so here we're going to look into Model Manager, and you can see in Model Manager we have the temperature in a tabular viewpoint. This could be output into Excel for any kind of post-processing you would want to do from that point, and creating graphs or anything like that from your results. And here we'll just highlight everything that's over 150 from the relays, and we'll just show these objects. So if we come back in here, we can see all of our hot relays, and we can kind of look inside, see what's going on with those. But now sometimes that's a little difficult to look at because that's not relative to everything. So we're going to bring in, now we're going to switch to set a critical temperature. And so something you do in ElectroFlo is set a critical and a warning temperature for every component. And we've now set these, and what that allows you to do is if a component fails at 125, that will be red, whereas a component that fails at 150, maybe it's at 130, but it's still going to be green because it's well within its range. And here we can see our hottest components, they clearly stand out, and so that really helps to emphasize the fact that, okay, this is where we have a problem. If you need to look inside of your model, you can obviously uninclude the case, and so here we're just hiding the case, so we can see everything that's inside of our model. And as we look inside, we can see that we have some traces that are in a little bit of trouble. Our board layer there is a little hot, and so that would need some work, even though that's not one of the hottest spots in the model. And then if you want to get that back, you can put the case, and we're just going to make that transparent so that you can kind of see everything relative to the overall model and see how that's going. So here we look at it, and you can see inside, you can see the troubled spots. And okay, so and from this you can take any kind of screenshots, you can take videos of that. Next we're going to look at the 3D plot for drawing onto CAD. When you bring stuff into eFlow, a lot of times it's defeatured, so it's not going to look exactly like it did in CAD. And in order to be able to create a nice image that looks exactly like your real prototype does, you can go through and map those results back onto CAD. And we're using some clever sort of tricks to make sure that that's as close as possible to what your real results are. We're not just saying if it's closest to this temperature, that's what it is. We're looking at the material and interpolating the results there. So with these results, there's another way of sort of emphasizing where your trouble spots are, and that's by using a user-defined fringe plot. So here we're going to set a max of 140 and a min of 130. What that means is everything under 130 will be blue, everything over 140 is going to be red, and there we can quickly see, okay, we have a few FETs here on this board that are in trouble, and we'll need to work with those, and everything else from this standpoint looks okay using this criteria. Okay, so the next thing to look at are some of the tools that we have for post-processing. And the first is a planar region. And what this planar region is, it allows you to look at what's passing through any plane in your model, or any 2D region in your model. So we go through and specify that region. And then once we do that, we can see the average temperature of fluid flowing through it, what's the velocity or mass flow rate or volumetric flow rate, the enthalpy of the energy transferring through that, or the conduction, how much heat is going through that area from a solid standpoint. And you can look at this for solids or for fluids. And another way of looking at things is that you can go through and specify a volumetric region. And this is obviously similar to the planar region, only now you can see what's the total power that I have for that area, or what's the average pressure in that region for either solids or for fluids. And then it'll show you also the volume and the mass as well. So now we're going to look at our external post-processor called ParaView. ParaView is an open source free software available to everyone. And from that you can write results straight out from ElectroFlo. Here we see a simple bus bar model. There's no CFD here, so we don't see any velocity vectors, but you can see an animation now of the temperature. And you can look at this from any kind of animation temperature. You could look at the voltage changing. You could look at how your CFD develops over time. And they have a lot of filtering tools that allow you to do more advanced work. Here we're just going to do a quick clip and look at a cup plane. But you could multiply different results together. You could create the heat fluxes and look at a heat flux plot. A lot of stuff, and then while it's running here, we can actually dynamically change what plane we're looking at here during the animation, and quickly switch. So that allows you to make some really nice videos.